Let's dig into the details of the proof of the Cut-elimination theorem. The proof takes a bunch of lemmas, and they're all proof transformations. We argue that if we have a certain deduction, we also have a related deduction, and all the proofs are explicit recursive arguments. What I mean is that each proof really tells us how to transform one deduction into a different deduction, and it does this by telling us, step by step, how to transform each rule. Let's start with this lemma as a sort of warm-up. If z infinity deduces gamma with bounds alpha, k, c, and delta is a larger sequent than gamma, then z infinity deduces delta with the same bounds alpha, k, and c. Of course, we could use a weakening rule to deduce delta, but that would require that we replace alpha with a larger ordinal, and it will be convenient later for that not to happen. And also this will be a nice illustration of what all these proofs are going to look like. The intuition is that we want to extend the final step to be a deduction of delta, so we need to add extra formulas to the conclusion, and we could do this by going through every step of the deduction and adding whatever formulas are needed to make this work. To make that precise, we give a proof by induction on alpha. We consider what the justification of the last sequent is. First, suppose we justified gamma directly using the true axiom. For instance, if alpha is 0, this must be what happened. In this case, there must be a true atomic or negated atomic formula in gamma. Since that formula is also in delta, z infinity deduces delta with whatever bounds, so certainly the same bounds. You might have thought, when we introduced the rules, that it was redundant to allow the true axiom to be a sequent when we also had the weakening rule. We could have defined z infinity differently. We could have said the true axiom only deduces a sentence, and that if you want a sequent, you combine it with the weakening rule. But we didn't define z infinity that way, specifically so we would get this lemma. Next, consider the case where we justified the last step using and introduction. So let's say we deduced gamma, comma, phi, and psi from gamma, comma, phi, and gamma, comma, psi, and that gamma is the subset of delta. We must have deduced each of these subdeductions with some bounds beta less than alpha and gamma less than alpha, so the inductive hypothesis applies. By the inductive hypothesis, we can also deduce delta, comma, phi with the same bound beta, and delta, comma, psi with the same bound gamma, and then the same and introduction rule gives us delta, comma, phi, and psi with the same bounds. That case wasn't all that interesting. We just applied the inductive hypothesis and used the same rule as before. To give a technically complete proof, maybe we need to go through all the other rules, but they'll all look just like that last case did. You apply the inductive hypothesis to the premises, and then the same rule gives you the conclusion you want. It would be really boring and not very informative to go through every case for every lemma. For all the lemmas we need, there's usually one or maybe two rules where something interesting happens, where something has to work out just right for the proof to work, and then all the other cases are apply the inductive hypothesis. In this case, the true axiom was actually the most interesting case, even though it wasn't very difficult. It was the important step in the proof because it was the one where our deduction system had to be defined just so in order for the argument to work. For future lemmas, I'm only going to discuss the interesting cases, and in the notes, I've usually written one of the uninteresting cases as an example. Z infinity, especially Z infinity with the bounds defined in just the right way, is kind of subtle, so you have to trust, or even better, verify for yourself, that I've actually recognized all the cases that really need to be checked carefully, and that all the cases I'm going to brush under the table really do follow easily from the inductive hypothesis. Next, let's figure out what to do about cuts over atomic formulas. The lemma we need is, suppose Z infinity deduces gamma, comma, phi, with bounds alpha, k, and c, where phi is a false atomic or negated atomic formula. Then Z infinity deduces gamma with the same bounds. Our perspective is that it's obvious when an atomic or negated atomic formula is false. So if we can deduce gamma, comma, phi, that means one of the formulas in gamma union phi is true, Phi is obviously false, so one of the formulas in gamma is true. The idea behind the proof is there's no rule in Z infinity which deduces phi, which puts a false atomic or negated atomic formula in the conclusion in a meaningful way. So what we'll do is go through the proof and just delete this false formula everywhere it appears. And since it's false, no one cares. All the steps in our deduction will still go through just fine. Formally, this means we proceed by induction on alpha. The interesting cases are the rules which could introduce phi at all. The rules where phi could be showing up in the conclusion for the first time. Those rules are the true rule again, and the contraction rule. If gamma comma phi is justified by the true rule, that means there's a true atomic or negated atomic formula in it, and it's not phi, because phi is false. So whatever this true formula is, it's in gamma, so we can also deduce gamma using the true rule. If the last step is contraction on phi, so we deduced gamma comma phi from gamma comma phi with bound beta less than alpha, we actually have to apply the inductive hypothesis twice. We apply it once to get a deduction of gamma comma phi, whose bound is still beta, which is less than alpha, so we can still apply the inductive hypothesis to this deduction of gamma comma phi, and we get a deduction of just gamma, whose bound is beta. And then, just to avoid bookkeeping complications with our bounds, we stick in a trivial weakening rule so the conclusion is still gamma, but now we deduce it with the original bound alpha. Those are the substantive cases. The remaining cases, all the other rules of Z infinity, they just use the inductive hypothesis in a straightforward way. We're going to give the full proof later when we have all the cases covered, but we actually already have enough to deal with eliminating atomic cuts. That is, we could go ahead and prove if we have a deduction with cut rank 1, where all the cuts are over atomic formulas, then we also have a deduction with cut rank 0, a cut-free deduction. Because we could go through this deduction, and every time we find a cut, we know it's between an atomic and a negated atomic formula. One of them's true and one of them's false. So we throw away the branch with the true formula, we take the branch with the false formula, we inductively remove all cuts in that branch, and then we invert away the false formula. And this is actually much easier than the other cases, the cuts over more complicated formulas. And it leaves the bounds alone. There's none of this recursive doubling of ordinal bounds, omega to the alpha stuff that we'll be seeing later.